Hi, I'm Tiago Garrett. I'll be presenting the paper Keep Your Friends Close, Leveraging Affinity Groups to Accelerate AI Inference Workflows. The context for this work is real-time AI inference workflows. So this is a very general representation of how a application of this type is deployed in practice. So usually there's a input stream of data. Then there's always some kind of load balancing that is going to spray the data objects to be stored and the requests to be processed. So and the infrastructure is composed of several nodes, and these nodes will have different they will be responsible for different things like a database or CPU-based tasks, GPU-based tasks, and each of these tasks, and they may have to communicate with other nodes to be able to get some data that is required for processing that task and for storing more things. And so this is a very general idea of how these things work in real deployment. But then the thing is, as these different nodes have to fetch data that are required from other nodes from other nodes to be processed, there may be some cache misses, and because then data has to be moved from one place to another in this infrastructure, distributed infrastructure. And this is very normal and it happens all the time. But our claim here is that for real-time AI inference pipelines, this can be particularly a bad problem. Because the freshness of this data that is coming and the size of this data is something new. It's a bit different from other stream processing applications that we are used to, because now its data is just bigger and the latency is still very important. So that's what we want to address here. And to give a more concrete example, so I'm going to use this real-time collision prediction application as a running example in this presentation. This is also used as the running example for the paper. So the idea for this application is that we have a camera in an intersection monitoring different actors, so like people and cars, and the pipeline consists of detecting these different actors, tracking their trajectories, and then predicting the future trajectory of each one, and then matching this predicted trajectories to see if there is any collision that can happen in the future. So this would be a presentation of this pipeline, like in a directed acyclic graph form. So you have a camera sending a stream of frames, and then there's this multi-object tracking model that is going to detect the actors and track their trajectories, and then for each one of these actors, as this a separate instance of the prediction model is going to run to predict the future trajectory of that particular actor in that particular frame. And then once you have all predictions for a particular frame, then you can run this collision detection to check if there could be any collisions in the future. So this is the idea of this application, this example application. And to see what happens, we took this application and we deployed it on Azure using normal, like standard technologies there, like Azure Machine Learning. We have several different endpoints with multiple instances to scale, and then we also used the Event Hub to send data between these different steps of our pipeline, and the Cosmos DB for storing intermediate data, so on. So I'm not gonna go into much detail because of time restraints. So what happened then? What we observed is that there's a lot of overhead caused by moving data around, especially due to cache misses, because as the load balancer on this Azure platform spreads these requests across the infrastructure, a lot of data has to be moved because the model has needed some data that is not there and needs to fetch it. So, and that's the thing. So this is kind of shows a bit. This is for one particular step of in our pipeline, and the gray, this is an end-to-end latency breakdown. So let's looking at just one of these bars. The gray bars here, the gray sections, they represent the data being moved, and the red one is the actual inference time of the model. So the bottom bar here, it's just fetching the video frame, so this cannot be avoided, but the other two, they can be avoided, because these are just fetching and storing data somewhere else that if it was already cached where the inference is going to happen, then we would have avoided it. So this is what we want to do here. And then we try to do that on our Azure deployment by actually manually routing the requests to where we knew the data was going to be, because we placed it there like manually. So so based on the ID of the different actors, like people and cars, we will always send data and the requests corresponding to that particular one to the same based on the numbers. And this worked. We got rid of those overheads, but the problem here is that this made our application very coupled with the actual infrastructure and the actual deployment. And this is a problem, because then for maintainability, and also because then the developer has to be aware of how exactly the infrastructure looks and how this is deployed. And in the case of Azure, another thing that we lost was the auto-scaling feature, because now it doesn't work anymore, because auto-scaling would increase the number of VMs, for example, or decrease depending on the load, and that just breaks our manual routing of our requests that we wrote there, and it just makes it very much harder. So we would like, what the problem we are facing here is that, okay, we would like to make everything automatic, and we would like the developer to be able to just provide encode his knowledge, because the developer knows exactly how different data and the tasks that are going to run on top of those data, how they are correlated and where they should be. So, but then there's no, currently in all these AI frameworks for development and the whole C platform, there is no tool to just encode this developer knowledge in a way that it's deployment agnostic, so the developer doesn't need to know how the infrastructure looks. It just says, okay, this is gonna be about person number 7, and then everything related to that, the hosting platform will take care of making sure that everything that is corresponding to person 7 is gonna be collocated. And so this is the problem: how to encode this developer knowledge, and so the pipeline can run very efficiently without transparently, basically. So our idea, the basic idea is very simple. We just label things. So every object that this should be stored has a label, and the task request has a label, and then with those labels, the hosting platform can know exactly where things should be and where things should run. So that's the basic idea. And we call our mechanism affinity grouping, and it has mainly 3 parts. So one is we have a tool that allows the developer to specify some logic that will attach a string, which we call affinity key, to any request to run a task for computation. And also the same logic will also attach the affinity key to data objects to be stored. And then the last part of the mechanism is that the hosting platform has to make sure that these affinity keys are used actually for the placement decisions. And then the assumption is that anything with the same affinity key is correlated. And some example of how this can be used is that, data objects with the same affinity key, they can be cached together. So everything that is needed for a task that is gonna come in the future will already be there. So there will be no wait to just bring and to cache something that is somewhere else. Another thing is that some task request that has the same affinity key will also be placed there. And then with all this we can avoid those overheads. And we implemented this in AI hosting platform called Cascade, which is developed within the same project that I was working on at Cornell University. So, and this is a platform that is targeted at low latency AI pipelines. So I invite you to check the paper for that as well. One specific feature of Cascade that is important here is that so Cascade is based on a key value store, and the idea is that and how the placement of these key value pairs, these objects is done is based on the key. So Cascade will just take the key of the object, hash it, and then decide where it goes based on the hash. So it's a consistent hashing mechanism. But that's also used to decide where computation is going to run. So when because the computations are triggered in the same way as stored procedures in a conventional database. So when a key with a certain prefix is put into the key value store, then operation is triggered, and the place where it is triggered depends also on the hash of the key. So that's we take advantage of that mechanism to implement our affinity grouping, and the way we do it is through regular expression. So the feature that is provided, the tool that is provided to the developer is just a regular expression. The developer will provide a regular expression that is going to be matched on the key, on the object key, and then the matching string of is going to be the affinity key. So the idea is that, so here is the prefix that triggers the computation, and this other part here is the actual key of the object being put. This is the regular expression that is provided by, so this is the logic provided by the developer, and then this is the affinity key. So basically this is extracting a portion of the key, and then any object that has this affinity key will be related. So in this case it's basically the actor in the video frames with the same ID. Doesn't matter the rest of the key, everything is gonna be placed at the same place. And this is important because in this particular pipeline is a good example, because the workload for the pipeline, it changes dynamically. So it's depending on how many actors are detected in the image, the number of prediction models that are going to run in parallel is different. So the workload is not predictable, and that makes schedulers not work that well. So and this will always work, because this regular expression is going to be applied to all the keys that are being generated in a step that the next one is already placed in the correct place, even though we didn't know that before the first step ran. So this is some results we got. So this is the end-to-end latency, and we can see that in green here with affinity grouping we got a much lower end-to-end latency, much more consistent as well, and this was true as we increased the number of shards, so as we scaled our deployment. So to conclude, we identified some inefficiencies in modern platforms to collocate data and compute, and then we proposed this mechanism that encodes developer knowledge and then allows the platform to collocate data and compute. And implemented this affinity grouping using regular expressions. And as the feature works, one idea is to automatically identify the best mapping between requests and then affinity keys. And also we have another idea is to investigate how a scheduler can better take advantage of this affinity grouping for things like load balancing and prefetching. Thanks.